My name is Sarika Janan. I am from Indian Institute of Technology. So today I am going to talk about multiplexing induced explosive synchronization, the work which I have done with one of my postdoctorate and PhD student, and it has recently been published as well. So explosive synchronization means which is something like first order discontinuous phase transition. Suppose if we have a network with the interacting nodes and they are interacting with some coupling strength lambda. So as you increase lambda, so in this R1 I will define later, they are order parameter which defines the coherence among the nodes in this network. So in the beginning when they were not interacting, it means for lambda is equal to 0, they were incoherent. And as you are increasing the coupling strength among the nodes, they start showing some kind of coherent behavior. And explosive synchronization means there's a jump. So as you keep on increasing lambda, so coherence was very less, and suddenly there is a jump to the coherent state. And this is the first order explosive synchronization which we refer as. So this is in the forward direction, and this is also associated with the hysteresis loop. It means that as you decrease this lambda adiabatically, so it keeps on showing synchronization or coherence up to a larger coupling strength, and then it goes to the, so this is the backward critical coupling strength, and this is the forward critical coupling strength with the hysteresis loop. So this is the chronological order of first order transition, which was in the business since long, like 20 years, but recently it has been given the name explosive synchronization. And experimentally also it has been demonstrated in circuit of Rossler oscillators. And why we are interested in explosive synchronization, there are certain examples which I have written here and which I am skipping now because the more like a theoretical modeling which I am going to present. So network science, or I mean to say explosive synchronization, so far mainly focused on one type of interaction among individuals, which is a standard type of networks here. First node is interacting with second, second is interacting with third with the same type of interaction. But now it has been realized that there may exist more than one type of interaction among the same unit, and that is multiplex network, and I will give certain examples. Like here, what does it mean? That first and second node has two different types of interaction can exist between the same pair of the nodes, or in the same network, one pair may interact with one type of interaction, another pair may interact with the another type of interaction. And this is a few examples of multiplex networks, like one very popular example which is very easy to understand, that is about the transport network. So cities in the first layer may be connected by train, and cities in the second layer may be connected by airlines or the bus routes. So activities in first layer may affect the behavior, dynamical behavior of the people or transport system in the second layer. So this is the multi-layer framework. And so these links are not the physical links, these links, vertical links are telling that how activities in first layer is affecting activities in the second layer. Okay. So multiplex network is a set of N nodes interacting in M layers, each reflecting distinct type of interaction among the same unit. And it has been shown that ignoring impact of multiplexity may result in wrong prediction for the behavior of the system. And this is one example. And what I am going to present today, that's explosive synchronization in one layer by appropriate multiplexing with a delayed layer. And this was the work which I presented last year, and that's why I have put. Yeah, so there I had last year I shown that how we can control dynamical properties of one layer with another layer, but with the different aspect. And now I am talking about this explosive synchronization. So now this is the framework. So suppose we have 3 layers network, for example, 3 layers or 2 layers network. So when we don't multiplex, I will present the model in the next slide. So when we don't multiplex, this layer will show simple continuous second order transition to the global synchronization. So there is no sudden jump. So without multiplexing, there is no jump. When you multiplex, then also suppose there is no jump. But as soon as you introduce delay in this layer, so one layer there is a communication delay. Delay, I mean here that communication delay, that how this node is interacting with this node. So as soon as one introduces communication delay in one layer, that induces explosive synchronization in second and third layer which is not even directly connected. So delay in one layer, that induces explosive synchronization in all the three layers, and this is the result. And now this is the model which is there. So for this I have taken chromato oscillator with inertia. This is one of the very popular model in nonlinear dynamics. This is the intrinsic frequency for the ith oscillator in ith layer. So you have, this is the intrinsic frequency, and this is the coupling term. So this second coupling term is intralayer coupling, and here you can see within the same layer they are having communication delay, so t minus tau. So dynamics of ith node at time t is affected by dynamics of jth node, that is its neighbor, at time t minus tau. Okay, and this is the diffusion term. So this is the intralayer coupling where neighbors are interacting with delay, and this is the interlayer coupling. So you have first layer like alpha layer is connected with beta layer. This is the coupling strength between two layers, and this is the one-to-one coupling between the mirror node. So this is interlayer and this is intralayer. This is the dynamics for second layer. Everything remains same except there is no delay. So we are introducing delay, intralayer delay only in one layer. Second layer remains as it is, and this is order parameter which I had plotted in the previous slide. So order parameter, it is only talking about the coherent. So if all thetas are same, this is R1 and R2 will become 1, and if thetas are homogeneously distributed between 0 and 2 pi, then R1 and R2 would be 0. And like why I have taken this second order chromato oscillator. So this is just one motivational slide which I am skipping. And the agency matrix of this entire thing. So right now this agency matrix, so this is the intralayer agency matrix, and this is a one-to-one coupling between two layers, but I can write down this is a supra agency matrix. So this is layer 1, layer 2. Layer 1 has this A1 is representing the agency matrix of layer 1. A2 is representing the agency matrix of layer 2. I is the unit identity matrix, which is talking about interaction between the mirror nodes. Dx is the coupling strength between two layers, and Ey here is the intralayer coupling strength, which is telling that relative coupling strength between these two layers. So this is just more generalized kind of model, which so we have control over Dx. So Dx is the interlayer coupling strength, and Ey is the relative coupling strength between two layers. So these two are the controlling parameters, and now these are the results. So here I have plotted lambda is the overall coupling strength in the network, in multi-layer network, and R1, R2, R1 is the order parameter for first layer, and R2 is the order parameter of second layer. So in the beginning, as you can see, when tau is 0, delay is 0, you have continuous second order transition to the synchronization. So synchronization exists, but there is a continuous second order from 0 to 1, R1 and R2 is going from 0 to 1. As we are changing tau, this is a delay, intralayer delay, one can see there is a jump. So this is the first order transition which is depending upon tau. So just by tuning tau in one layer, actually we can control the nature of synchronization in all the layers. So as you keep on changing the tau, you can again come back to the second order, again you can have jump, again second order, the small jump. So you can have complete control over the dynamical nature just by changing the tau of one layer. So please note that second layer we are not changing anything. It's the first layer where we are changing, and we are controlling second layer. So that is something is, yes. And this is all the phase diagram. So this is frequency of individual oscillators. So one can see that in the beginning frequency was distributed. So this is second order phase transition where one can see a different type of, this is a route to the synchronization, which is different in this explosive synchronization than in the non-explosive. In explosive synchronization, you have small clusters which form and suddenly they make big cluster, whereas in the smooth second order, you have more and more number of nodes keeps joining the giant cluster, and then you have the complete synchronization, which is depicted here. And we have some analytical understanding also for this. This is very easy to do actually for, so this analytical calculations are easier, but we are not able to solve it for the critical, we are not able to find out the critical coupling strength for the transition. What this analytical calculation is telling me that my frequency that depends upon tau and this intralayer coupling strength. So let me now just show this result of, so this analytical calculation which we have done, very simple analytical calculation where we are just able to show that frequency that depends upon tau and then frequency which in turns decide that whether we are going to have first order or second order transition. And we can see with tau this frequency of oscillators which is showing some periodic kind of behavior, and depending upon how far it is from the initial frequency, you get either the first order or second order transition. Okay. So, and these are for different networks. So these slides are to show that results are very robust against the change in the network structure or average degree. So whatever network parameters we take, we are always able to show that there exists the explosive synchronization depending upon tau and interlayer coupling strength.
So time for some questions. Yeah. One question.
So the way you have introduced the multiplex, it looks like delay is there only in one type of interaction. How is that possible? If it is a transmission delay,
so
you are saying only one type of interaction has delay, the other two types have no delay.
No delay, or they may have negligible delay as compared to the, like for example, like trains, they run quite in delayed manner perhaps, but air connectivity in general, they are not much that delay. That can be one type of example which I can give, but one layer has more delay, another layers may have delay but which you can neglect.
But in that context, what is the meaning of that interconnection?
Interconnection, that's what I said.
Without any delay.
Any physical meaning. Interconnection is only telling that how activity in one layer is affecting your activities in another layer. So it does not have any physical meaning as such, because this is the same neurons, for example. So how functionality of one functionality affects the another functionality. This is the meaning of interlayer. So this is not a physical connection.